Hey guys, so we're talking about electric fields today. So we're going to draw a few here. First of all, we got to understand the different structures of a uniform and non-uniform electric fields here. Non-uniform fields are essentially fields around charges. Okay, so if I've got a charge that's negative, all right, then it will have a non-uniform field around it pointing in like this. And the reason why it's pointing in, right, is let me get rid of these outer arrows. Ooh, ooh. Well, let me redo all of this field. Ah, that works. If I've got a negative charge, the field's going to point in because the rule that physicists have made is that your field lines point in the direction that a positive charge would go if placed there. Okay? And so if I were to place a positive charge anywhere here, it would get pushed in. Okay? And the reason why it's non-uniform, this field, is because we would use Coulomb's law to figure out the force electric on it. And as you know, that as you move in from, like, for example, here to here, the field strength is different. Okay, so it's non-uniform. All right. Conversely, a uniform field is uh, made by having a plate, okay, and then another one. So these are metal plates here, okay? These guys in this area, these guys are metal plates here and here. And you attach them to a battery, all right? And if you have a negative side to your battery and then a positive side to your battery, here's your negative side, here's your positive side. Then this plate becomes negative and this plate becomes positive on the top plate. The bottom plate would be negative. The reason being is because your battery, because this is the negative terminal of the battery, it's basically a big reservoir of electrons. So you put a neutral metal plate down here, and all these electrons, a lot of them, not all of them, but quite a few of them would escape into here, creating an overall negative charge in the bottom. All right. And the same with the top there. All right. And so you end up with things like that. Okay. And now, if you look closely, I've drawn arrows that go down here because if I were to place a positive charge in this inside here, it would get pushed down. All right. And this is a uniform field, is because as it turns out, everywhere uh, in this area in here, the field strength is completely the same strength. Okay. And how do you find that field strength? That field strength is found by doing delta V over R. R is the distance between the two metal plates, okay? And delta V is the strength of the battery, or the, how strong of a battery you hook up to the things, all right? So now let's do a couple of example questions here. So, by the way, those are uniform and non-uniform plate fields. These are sometimes called the parallel plate apparatus or system, or parallel plates. When you're reading questions and you see these words parallel plates, you know you're dealing with a uniform electric field. Here, let's answer this question. What is the electric field strength 0.6 meters away from a charge? The charge is given, and this is in coulombs. All right. Well, basically, we would just use this formula here because this is it doesn't say that it's a parallel plate, so you just assume that it's a point charge. Excuse me. And so, as a result, you've got that. So I basically I'm going to be using this formula up here, okay? And I am going to go ahead and type in those values. And this is a pretty simple calculation here. Hopefully I typed that into the calculator once. I didn't do a double check. Or hopefully I typed it in correctly. So there it is. Part B, what amount of force would a -2 Coulomb charge placed at that point experience? Okay. All right. So now basically it's like, well, we've got sort of a location in space. I'll draw this out. We've got our first charge, which is 1 times 10 to the -3. And then over here, we're about 0.6 meters away. Now, all of a sudden, I'm going to place a -2 Coulomb charge right there. And we want to know what's going to happen. What force will it experience? First of all, we know that it's going to get pushed that way. So this is positive. This is negative. Over here, we got a positive. Oh, shoot. This one's negative, right? And this is a negative, and that's positive. And so, therefore, they're going to attract each other. So this is going to experience a force in that direction. We'll call it Fe, force electric, might as well. I'm actually going to use Coulomb's law for this. And so I'm going to do K, Q, Q over R squared, and that's my force electric. And so in the end, it's going to be 9 times 10 to the 9 times 1 times 10 to the -3 times -2 over 0.6 squared. Okay. And it looks like we're going to get, well, if that number up there is right, we're going to get 24 or 4.8 times 10 to the 7 newtons. All right. And you get a negative value here, meaning that it goes in the opposite direction of the field lines. Okay. And why does that make sense? Because this over here, this guy was our original charge. Here, I'll do this in green. This guy was our original charge. And so he's got field lines going out like this. And so basically he's got some field lines going out like this. Then this guy comes in here. You put some calculations. You get a negative force on it, meaning that the force is going to be pointed in the opposite direction of the field lines. And so that's why you end up with a negative answer here. Okay. Let's look at part C. If the charges move 0.2 meters closer together, how many times would the force change? By how many times would the force change? Okay. What you can do, I suppose what we can do is we can figure out this new force electric. Well, force electric 1 is KQQ over R squared. Force electric 2 is KQQ over R squared. This was R1 and that's R2, right? And if I want to figure out by how much they change, what I'm going to do is I'm going to make a ratio from these two guys. So I'm going to go ahead and put these two equations in a fraction here, okay? And I'll go ahead and erase these equal signs because basically what I've done is I've placed, what I'm going to do is I'm going to do it more officially like this. Force electric 1 over force electric 2 is going to give me the ratio of the forces, okay? Oh, and honestly, since they want to know by how much it's changed, it might be more advisable for us to put the force 2 on the top and force 1 on the bottom, which is going to be a 1 here and a 2 there. Okay. And so now, basically, well, this is actually a pretty interesting thing because look at this. If you look at this algebraically, my k's cancel, my q's cancel, And I'm basically left with 1 over R2 squared divided by 1 over R1 squared. And so if you think about that, it's just 1 over R2 squared and 1 over R1 squared. And if I kind of take a look at this, I'm going to multiply by the reciprocal, because dividing by a fraction is the same as multiplying by the reciprocal. I basically get R1 squared over R2 squared, and R1 was, remember, 0.6, and R2 is, if the charge moves zeros closer together, so that would be 0.4 squared, okay? And now if you figure out what this is going to be 0.36 over 0.16, and I don't know what that is. It's going to be like, I don't know, 2.2 times greater. All right. Maybe it's not 2.2. It's probably like 2.1. But whatever. That's how many times greater it's going to be. So there was some examples of a uniform electric field. Sorry, that was a non-uniform electric field. Here I'm going to do uniform electric fields. Perhaps I'll make I'll go for it. So combine projectile motion with a uniform electric fields. So success criteria is to navigate with clarity a complex multi-step question involving numerous physics concepts. Oh my, this sounds crazy. All right, so look at this. We've got some kind of crazy diagram here. Looks like we've got some kind of electron. It's shot into here, and it goes down like this, and it somehow leaves, okay? And we'll see what kind of question we're asked here. Looks like we've got a length here, L here. There's lots of stuff going on in this question. Basically, why do we know that this is going to happen? Because this guy gets shot, and he's an electron, so he's going to get repulsed from this plate and attracted to this plate over here, okay? And so that's kind of the idea. And as it turns out, this is basically like a projectile motion question. So let's say an electron is fired horizontally at 2.5 times 10 to the 6 meters per second forward, where it enters 0.1 meters below the top negatively charged plate in a horizontal plate, parallel plate apparatus that is 0.075 meters long, okay? So it looks like we've given our length here, okay? And the distance between the plates is 0.04, and their potential difference is 120. All right, so we've got about 120 potential difference there. Does the electron escape the other side? Oh, so the question is, does it get to the other side here? Well, how are we going to figure this out? Well, basically the idea is like, does this thing get pushed down so quickly that it hits, or does it not, or does it escape the other side? Basically, is kind of the idea there. All right. So what I'll do is I'll think about this. How are we going to do this? Let's do projectile motion on this. And basically, what I want to do is I want to figure out, well, how long is this thing in? How long is this electron inside the parallel plate apparatus? Then, once we figure out how long it's inside there, we can say, all right, well, it's going to experience a downward force for that length of time. So it's going to experience some kind of acceleration, and it's going to get pushed down. If it gets accelerated so much such that its vertical displacement here is greater than this distance here, then it hits the other side. Okay, I think that's how we'll approach this. Then if the vertical displacement is less than our little leeway, which appears to be uh, the difference between these two values here, okay, those two values, so it's about 0.3 is what I'm looking at. Okay, let me erase all this stuff, and I'm going to go with we've got 0.03 meters of leeway there. All right. So basically, I want to figure out how long the thing is in the apparatus. Well, that's pretty easy because delta is, no, that's not what I want. I want to write velocity is equal to uh, distance over time. And this is in the x direction. Notice I've got an x right there. Okay. Um, And basically, what I can do, well, I know that this is the velocity right here, and I can figure out, well, how long it's been in there for. Look at that, because I know how far it can travel, which would be this right here. So we're going to go ahead and do that. It's going to be delta t is equal to the distance that it travels horizontally over the velocity that it had, or 2.5 times 10 to the 6 meters per second. This is how long it's actually in the thing there, all right? I actually think I'll go ahead and calculate this value, but well, let's assume we got that value. I'll calculate it later. All right, so basically we're going to go ahead and say that's how far it went, okay? Oh, sorry, that's how long it is in the thing for. Now what I'm going to do is I'm going to say, all right, in my y direction, I've got a initial velocity y of 0. I've got a delta t of whatever that answer is up there, okay? So 0.7, sorry, 0.075 over 10, sorry, 2.5 times 10 to the 6. 2.5 times 10 to the 6. Okay. I got to figure out the acceleration of this thing. And if that's the case, then I'm going to try and figure out the vertical displacement. And then I'm going to compare this vertical displacement and I'm going to say, is this thing greater than 0.03? Question mark. So I'm going to get an answer here. If it's greater than 0.03, then therefore the electron hits the bottom plate. Okay. If it's not greater, then the electron doesn't hit the bottom plate. Well, first of all, we got to figure out the acceleration of this electron. Well, don't forget that the electrical field strength is equal to the delta V over R, right? Which is, what is it going to be? 120 over the distance between the two plates is 0.04. Okay. And so what are we looking at here? 30,000? Is that right? No, that's not right. Maybe it's 3,000. Whatever the case, we've got that. Then we know that the force electric is equal to the field strength times the charge of an electron, which is also equal to the mass of an electron times the acceleration of the electron. That's Newton's second law, okay? Remember, force electric is equal to field strength times charge, okay? And also force is equal to mass times acceleration. Well, what's the mass? Well, we're dealing with an electron here. So therefore, I can figure out the acceleration of this thing by essentially just taking this value. So if I just do a little bit of algebra here and I solve for acceleration, I'm going to get basically the acceleration is, let's go with this color. Acceleration is field strength times q over the mass of an electron. And remember that field strength is 120 over 0.04, or delta V over R times q over the mass of the electron. And that's basically our acceleration. So it's basically delta V times R over q divided by the mass of an electron. So there we go. We've got this, we've got that, and we've got that. Okay. So now I want to figure out my vertical displacement. Remember, my displacement in the y direction is equal to the initial velocity times the time plus 1/2. I think it's a plus. Hopefully it's a plus, not a minus. Pretty sure that one's a plus. Plus 1/2 delta time squared. Okay. Well, this is kind of convenient because my initial velocity is 0. So there we go. We got a 0. All right. So therefore, the distance that the thing moves is equal to 1/2 times the acceleration, which the acceleration is, remember, delta V times R over Q over mass of the electron times the, you know what, I'm gonna change this. Remember, so dividing by the mass of electron is basically the same as, let's see, multiplying by the reciprocal. So yeah, you basically just take this and we're going to take this and we're going to take delta VR over QME. All right. You probably can't see that very well. So this is delta VR over QME. That's my acceleration. All right. And I'll go ahead and write that right here because that's just, it was getting a bit crazy. So this is delta VR over QME. That's my acceleration. My time, what was my time? Remember, my time was this. And so that's basically just the length of the plates, which is L, divided by the velocity in the x direction. All of that squared. Okay. And I'm going to go ahead and calculate this off camera. I'll try and do it once or twice just to make sure, or more than once, just to make sure I kind of get that right. I'll be right back. All right. So I calculated that. And yeah, it looks like we've got 0.47, so about a half a meter. So it appears that it appears that the electron does hit the bottom. So it kind of like goes boom really fast in there. You kind of see what I'm saying? So that's it. So does the electron escape to the other side? The answer is no. All right. Oh, by the way, I did mess up the thing there. I don't know if you guys noticed on the video, I had my Q and my R messed up. Over here, my Q and my R were okay, but then over here, I switched my Q and my R. So then my Q and my R got all messed up over here, but now in this calculation, it's okay. So my Q and my R are in the correct locations over here from what I can see. All right, so there, it looks like the electron does hit the bottom side. So therefore, we're going to answer this question. If it does not go through find the impact velocity and its horizontal deflection. Okay? So let's go back up to our drawing here. Essentially, what's going on is this guy is going to go whammo. He's going to hit there really fast. So I want to figure out what's the velocity, what's the impact velocity that this thing has. It's got a vertical component and it's got a horizontal component, right? And that's going to be its impact velocity. This is Vx and this is Vy, okay? And then I should be able to find out the impact velocity, all right? And I want to be able to find out also how far it goes as well, all right? So what we can do is we can do those calculations, all right? So let me just go ahead and redraw this over here. So basically what we had is we had an electron that comes down like this really quickly, and it went a total of 0.03 meters, okay? We know its acceleration. We know that it had an initial velocity of 0. We know that its acceleration is this thing up here, delta V Q over R M E, okay? We know that its vertical deflection was 0.03. I can figure out how far it went, okay? Sorry, how long it was actually in here for. All right, and I'll go ahead and use, let's see. You know what else? You know what I'm going to do is I'm going to find its final velocity first. So I'm going to say that the final velocity y is equal to the square root of the initial velocity y squared plus 2 acceleration times the delta d. And so in the end, the final velocity y is equal to the square root of 2 actually, you know what? I think I forgot to multiply this over here by 1/2, but it still doesn't. So this should be half of this, 0.2 something or other, 24 ish. Still, it doesn't. We're still doing okay here. So because this is 0 right here, all right. My acceleration is my delta V Q over R M E, and my displacement is 0.03. Okay, so we can figure out my final velocity y. What is my final velocity y in the drawing? That's basically, remember, if I zoom in on this picture, my impact velocity is kind of like the velocity with which it hits this thing. It's got a horizontal component and it's got a vertical component. This is my final velocity y, which is basically this number here. We can figure that out later. And my horizontal component is simply just Vx. I already have that. And I can actually just figure out the actual final velocity by doing the square root of Vx squared plus Vfy squared. And there it is. And I can actually figure out the angle of this by doing the tangent inverse of the final velocity y over the velocity x. And so together, this is essentially my final velocity. It's the impact velocity, where this is the magnitude, right here, this is the magnitude, and this here is the direction, okay, or the angle, all right. So there. We what do we want to find out? We want to find out how far it went. We want to find out how far it went. So we want to find out this value right here. This is going to be a delta dx. All right. So my delta dx is going to be the following. I'll do it in green. No, I already used green. Let's use purple. All right. So to find the delta dx, basically, I need my Vx equals delta dx over delta t, right? Because in this direction, there's no acceleration. Okay, remember my electrical force is pointed always down in this example. Okay, so there it is. My delta dx is simply going to be the velocity in the x direction times the time. Okay, but the time can be found by analyzing this information over here. All right. And so remember, to figure out the time, I'm going to go ahead and say that the time is equal to the final velocity y minus the initial velocity y over the acceleration. And so that's equal to the square root of 2 delta vq over r me times delta d y. Okay, this is, by the way, a y, over the acceleration, which is delta v q r m e. Okay, which is going to be that as minus 0 right there. Awesome. All right, so that's pretty cool. As it turns out, you can actually save yourself some calculation here, and this little square root will cancel with this, leaving you a square root on the bottom. So it's actually just going to be 2 delta dy over the root of delta vq over rme. Okay. Otherwise, you can just calculate the whole thing out. That's the time. This answer gets placed over here, right there. Okay. That's some crazy calculations. I probably will pass on doing those because it's getting late over here, and I'm sure I won't plug it into the calculator right anyway. So basically, the rule of thumb for these questions is you're going to be employing projectile motion, okay, for one of these guys. This is a typical, a classic question that'll probably show up on the test, where you're basically going to be wanting to employ some projectile motion stuff, just like this stuff down here. But the only real difference is that the acceleration can be found by sort of doing this thing right here. Okay. Yeah. Doing that thing. All right.